Hi, Oscar. Hope you're doing well. Hello, Alicia. Coco, you're in the wrong class. You missed your live stream. It was earlier today with the 8th grade class when we normally meet, 5th period. So please watch the video, Coco. Okay, hello, Ellie. Hello, Penelope. One, two, three, four. So there's others coming on. Others say hello when you join up, and I know who you are. There's Chelsea. There's Errol. Dynamite. There's Amina. I got you, Alicia. Yeah. And there's Aiden. Good. That's about half of us. So let's get the other half here. We can start up. There's another one. Hello, Bella. I need a calculator. So do you. Grab a calculator if you don't have one. Who else I got? Louisa's here. Good, Louisa. Hey, now we're 2/3 of us here. I like it. Still need 5 more. Let's see. Give another minute or two and see if some show up. Well, I guess they're late then. Okay, so my people, let's spend the first part of the hour taking your questions on book problems, okay? Presumably chapter 1 of the new book. If it's older than that, you maybe want to just contact me by email. And I'm still working on that old number 11 one, but I'm not getting the answer the book got. So I don't know if they're wrong or I'm wrong, but I may not worry about it at a certain point. We do what we can, okay? That's certainly one I will not grade when I grade them, your books someday again. Theoretically, we're going to see some of you next week for teaching, but I think that's still up in the air. We'll see what happens next week. I don't have an answer for that yet. It's still being worked out. So we'll see what we do. Okay. Okay. Anybody else there? All right. So let's open it up. Any questions you've got so far on chapter 1 material that you'd like to talk about together? And Antonine is here. Good. Thank you, Antonine. And write you down wherever I put that list. Right here. And Bella has one already. Good. So I got page 12. Number 3. Thank you, Bella. Let's have a look. Number 3's got a reaction and it's got a graph. And it says, recall the discussion of instantaneous rate earlier in this section. Determine the instantaneous rate at the following times. Okay, an instant after 0 minutes. This is the initial rate. And at 1 minute and at 4 minutes. How do these rates compare? What do you suppose causes this pattern? Okay, so let me open it up to you. Little suggestion. So to do part A, everybody have a look. To get the instantaneous rates, what do we got to do? So help me out a little bit. What do you got to do? And I'll refer back to where Cheryl did this. Okay, I'm waiting for some of you. Thank you, Amina. Good. Okay, that's what I would do too. So what you're going to do for each spot is you're going to get, at least as far as I know, the slope of the line at that spot. So at each location, and what do they want? 0 minutes, 1 minute, 4 minutes. Okay. So it just after 0 minutes at 1 minute at 4 minutes. Okay. Draw a tangent line each of them. So you're going to get a tangent line at right after 0, at 1, and at 4. Okay. 3 different tangent lines. I'll show you how to do that. Tangent line and get slope of that line. Remember, slope is rise over run. And don't just count boxes like my 7th graders do. Okay, you got to use the numbers on the side, right? Get a slope to have the instantaneous rate, or rates in this case. Okay, so again, I'll kind of sketch theirs. Their graph looks something like this. And let's say we're going to do the one at 1 minute. So we're going to go to 1 minute. And we're going to go up, find that spot, and then draw a line perpendicular to the curve at that spot. Like that, okay? And then get the slope of this line. And that slope is your instantaneous rate. So that's how you do A. Let's look at B. How do the rates compare? Well, guys, you can guess just by looking at it. How are the rates going to compare? Are they going to be all the same or different? And if they're different, are they increasing or decreasing? What's happened to the slopes? Thank you, Mina. They're different slopes and they're decreasing. So we got decreasing, instantaneous slopes, instantaneous rates, sorry. And it says, what do you suppose causes this pattern? So what could be causing the pattern? Good, a lot of you got that? Okay, thank you, Lola. I'll check in. And while I'm writing her down, you guys think about my question, see if you can answer it. So what could be causing the pattern to change? In this case, to decrease. Look up at the reaction to help you answer that. So look at the reaction up above. What could be changing to change the rate? There may be more than one answer to this question, all right? It may not match Cheryl's answer, but I can think of one thing just by looking at the equation. The graph curve is becoming more level at the top. Exactly. So, and why? Why is that? Why might the graph be going like this based on the reaction? Hint, the calcium carbonate is a solid. That's doing nothing. Running out of a reactant. Good. Which one are we running out of, Oscar? Or at least, which one is the concentration changing? And by the way, it's decreasing. So we're going to have a lower and lower rate. Why? What else is getting lower and lower? Look at the reaction. Good. HCl. Now, finish that, somebody else. What about the HCl? What's changing? Make a little sentence or phrase, okay? What's changing about the HCl? Right, it's being used up. So let's use some chemical words. What's happening to the concentration of the HCl as the reaction goes on? Amina, that may be true. We don't know that for sure. This may not be the whole reaction, but what's happening to the concentration of the HCl? Okay, there you go. A couple of you got it now. It's probably a decrease in concentration of the acid. Why? Because it's being used to react with CaCO3. So it's less and less strong. So maybe you started, well, I'm going to make something. Maybe you started with 2 molar. Over time, maybe it's down to 1 molar, 0.5 molar. You know what I'm saying? Okay. And I hope that helps with 3. Are there other ones, either questions on 3 or are there other ones we'd like to ask about in chapter 1? And I'm going to make a little board space to do that. So while you're thinking, I'm erasing. And assuming we're not interrupted by Wi-Fi, I'll send this out to you, this live stream via Google Classroom again, in case people missed it, because I know some of them still are not here. Oscar says, can you write out how you would answer B? Well, yeah, okay. How do the rates compare? As time progresses, what happens to the rates? So as time increases, the instantaneous reaction rates decrease. Why? Probably the HCl concentration is what? You can fill in the rest, okay? As we said the rest. Emil, you're in the wrong time and place. Emil, our class was at 11:30, so you missed it. So go back to the Google Classroom and find the YouTube and watch that, please. This is AP Chem, so you're in the wrong spot. So watch the YouTube, take notes, mail me your notes, email me your notes. Okay, anybody else? Another one we'd like to ask about, chapter 1, book 2. If not, it's okay. We got certainly plenty we can talk about because we got a lot of still chapter 1 knowledge that you need to know to do more of it. Okay, I'll assume that's either haven't gotten that far or don't have any questions, so that's okay. So I'm going to put that aside, and I'm going to start with what I gave you last time. What word is that right here? Concentration. Concentration, Bella. So then you got to fill it in. The concentration is doing what over time? What would make the most sense? Okay, when last we met, I asked you to figure out, you're welcome. I asked you to figure out a rate, the reaction order for some chemicals. So let's do that. Okay. So from last time, I want the order of ClO. Well, let's do F2 first. F2 is what order? Okay, what did people get? F2, first, second, zero, first or second order. What was F2? So look back on hopefully the problem you finished up for me last time. Yeah, good. Aiden, Isabella, good. And Alicia, good. It's first order. Let's see how that can go. All right. So compare it. I'm going to compare experiment 2 and 1. Here, let's make that a little more legible. So here we go. Experiment 2 over 1. Well, I got what? I got 0.4 molar over 0.1 molar. Well, that's easy. That's 4. Okay. Then on the rates, I got rate of 2 divided by rate of 1. I got what? 9.6 times blah, blah, blah divided by 2.4 times blah, blah, blah. And that equals also 4. Is that right? No, I screwed up. Oh, man. Okay. David Vilcius, you're in the wrong class. You're supposed to be there at 11:30. So go to the Google Classroom and watch the video. You missed it. But you're in AP Chem, the wrong place. Sorry, AP Chem students. Okay, so, yeah, I screwed up. So it's 2.4, but I should have done 1 and 2. So let's make that, or sorry, 1 and 3. Okay, so try again. So it is 2 over 1, 0.20 divided by 0.10 is 2. And then the rates for reaction 3 and 1 are in ratio 4. And so you kind of say, okay, that means I got 2 to what power is 4, and obviously my power is 2. Yeah, well, I'm not doing this well today. I'm so sorry. It's not 2, it's 1. So how did I screw this up? I'm sorry, my mind is on a couple other things today. So what did I do here wrong? No, it's correct. I want 4. So I did it right the first time. That was stupid. So I do want 4 here. And I want 1 and 2. My apologies. Okay, so it's 2 and, or it's 4 and 4. 4 and 4. So 4 to M is what power? Well, obviously then it's first order. So 4 to the first power is 4. So it's first order. So we're going to go like this. We could go F2 to the power of 1, but you don't have to put a 1 there anyway. Okay, what about the other one? This is the harder one, ClO2. Oh, okay. Oscar's question. Why do you use experiments 1 and 2? Here's why, Oscar. I'm going to just hold this up and hope we can see it. Okay, you see how 1 and 2, Oscar, they got different concentrations of F2, but they got the same concentration of ClO2. So that's not varying. You need to have just one variable varying at a time. So you need to keep one constant if you can. You can't always, but here we can. So that's constant. So I'm going to use the 1 and 2. So that goes 1 to 4, and this goes a 1 to 4 ratio as well. So try and pick them where 1 is constant. Now we can't do that for the other one, ClO2, but we kind of have it figured out if you think about it. So I'm going to erase this because I need the board space for ClO2. So what order did you guys get? What order did you guys get for ClO2? We'll figure out the logic together, but let's get your guesses first, or your determinations. The order for ClO2. Bella got 0. See what others got? Oscar, second order. Okay, thanks, Aiden. We'll take a look at how we do it in a moment. Anybody else, do you get this? I should have a bunch more answers. Second order from Amina. Okay, the answer is no. No. All right, let's do it together. It's a little harder, but it's not impossible. And this is the kind you're going to find on the AP, not the easy kind. So I gave you a fairly easy one, which was, what did we come up with? First order, right? Okay. Now, look at reactions 1 and 3. Remember how I said to Oscar a minute ago, 1 and 2 were nice because it was only the F2 varying? We don't have that for ClO2. We have only 1 and 3, and 1 and 3 have 2 chemicals varying. 1 and 3 have the ClO2 varying from 0.1 to 0.01 to 0.02, and then the F2's varying from 0.1 to 0.2. But what we do have is more important. We've already figured out that the F2 is first order. Okay, so listen carefully. Okay, and this will answer, Aiden, your question, how to start this. And this might be Amina who's going to tell us right here. Yeah, good. Okay. Yeah, I think you're on the right track, Amina. Okay, let's lay it out for everybody a little bit. I got F2 is first order. So in experiments 1 and 3, if it was only F2, rate should be what? So think of what I'm asking here. Okay, look at what we did. When we went from 1 to 2, when we quadrupled the F2, we quadrupled the rate, 1-to-1 ratio. Well, if I double it from 0.1 to 0.2, so I'll do this way, 0.2 molar to 0.1 molar, then obviously, what should be the rate on top? It was 2.4 times blah, blah, blah. Well, on the top, it should be double that. It should be what? What's double 2.4? Should be, if I could write today, 4.8 times 10 to the negative third. But it's not. It's 9.6 instead. So the other chemical must be doing what to that again? So what's the relationship between 4.8 and 9.6? In other words, what's the ClO2 responsible for doing when it doubles? Notice it goes from 1 to experiment 1 to 3 by going to 0.01 to 0.02. Yeah, it's multiplying by 2. Good. No, it doesn't triple. Doesn't triple. So 1 doubling in the experiment 3 rate was due to F2 going from what? 0.1 to 0.2. But there's another doubling, and that must be due to what other chemical? The ClO2, the only other one we got. So ClO2 doubling from 0.01 molar to 0.02 molar causes essentially the 4.8 times 10 to the negative third to double again. Okay, and if I double this, if I double the ClO2 and I double the rate, then that's what sort of order? If I double one and the other also doubles, it's what order for the ClO2? Let me say that again. I'm doubling the ClO2 and the rate also doubles. Why? Because it doubles once due to the F2, but another time due to the ClO2. So what order is this sucker, the ClO2? Okay, Chelsea's got it. First order. So it's going to look like this. ClO2, also the first order. Okay? Okay, so write the rate law. So rate equals K times F2 to the first order, but I don't have to put 1, do I? Because math 1 is the same as putting nothing, times ClO2. So there's your rate law. Okay? And that's quite often what they want on the AP is for you to figure out your rate law. Okay, I don't want to lose you, but I really got to have all of you think and make sure you can do that mentally, because this is what they're going to have you do. They won't give you one just as easy as the F2. Everybody should have gotten that one. When this increases by 4, the rate increases by 4. First order, that's easy. But when this one doubles, the rate should have also doubled. Why? Because it's first order, because we learned that from experiment 1 and 2. Should be 4.8, but it's not. It's double that. So one doubling would make it 4.8, but the other chemical changing must make the other doubling. And what did the other chemical do? It doubled as well. So I got double doubles. Okay. One chemical doubling must have made the thing double once. One chemical doubling must have made it double a second time. Notice, this only works, folks, if you do the one first. That's an absolute. You have to have one that's an absolute, where I know in experiment 1 and 2, the concentration of ClO2 remains constant. And they will always give you at least one chemical where that's true. Okay? Then you can see what varying the other does to the rate. Okay, let's see if you got questions on that. I'm going to give you another one because those are important. Aiden asked if there's math behind it. Probably there is a math way to be behind it, but I generally just explain it in words when it's that complicated. Aiden, if it's like the straightforward one, like the one we did the first time, you can use the math way. David Vilcius, again, leave my AP Chem class. I'm sorry. You're in the wrong class. Go and watch the video that you missed because you're here at the wrong time. The video is in Google Classroom in the stream. Go watch it, take notes, send me a copy of your notes. Bye. Okay, on that note, so Aiden, there's probably a math way to show this. I think I did it the best way I could. I showed doubling it should have given me that, and then I would have said in words, doubling it, doubled it again to give me 9.6 times 10 negative third. And the second doubling was not there. Okay, very good. Good. Okay, I got Anne-Sophie with us as well. All right, so I'm missing 2 of you. Right. We're not going to do it because I have other stuff I want to do, but what if I ask you to find the K value? Look at this. What could I do to find the K value with the data? Can somebody just type that in real quick? What if part B was use the rate law to find the K value? Who remembers from yesterday? What do you do? How do you find the K? You got to use the data. Raise your hand. Good. Lola's got it, as does Amina. You plug in numbers from the experiment and solve for K. Exactly, Lola. And it can be either experiment 1, 2, or 3. It doesn't matter. They'll all have the same K value, so it doesn't matter which one you use, okay? Okay. All right. Okay. I don't want to do that, though. Okay. Instead, let me see where I left off yesterday. And we probably want to move into some new ideas, but we're not moving very far. I want to do another example with you. And let me see if this is one I want to do. Yes, this is one I want to do. Okay? All right. Okay, anything else before we go? No, just more correct answers. Good. Good. Yeah, thank you. Okay, so here we go. Erase, and we get to try a new one, okay? This time, I'm going to give you the order, and you're going to use the idea, okay? So please have handy your equations from yesterday that I gave you. So hopefully you still have your notes from yesterday. Okay, so here we go. N2O5 decomposes in a first order reaction with K equals 0.35 per minute. You can also put minute to the -1 if you like doing it that way. A, find N2O5 after 4.0 minutes if we start with 0.0, sorry, 0.160 molar N2O5. Okay, so it's first order. So either on the given information sheet on the AP or today in your notes, you've got to find that first order equation. Okay, I'm going to use the one that I like. Okay, so here we go. For A, let's change colors. I like this version. The natural log of the original, so I'm going to call it C original over C at time t equals K times t. So look at all the stuff we know. It's a lot. Okay, here we go. So natural log of, and you want to put the equation like I do and then fill it in. So don't be sloppy. So your original was 0.160 molar. The amount of time t, that's what we want, isn't it? So that's going to be my amount of stuff at time t equals my K value, wherever it is, there it is, 0.35 per minute. And now you know why it's per minute, because we got to multiply by the time, which is what? 4 minutes. Whoops. Not meters, minutes. Does that make sense? Okay, now, what do I do? Yes, I will save this video, as long as it doesn't get interrupted. I hope my Wi-Fi doesn't get interrupted. If it does, I got to kind of destroy it. What can I do to undo natural log? So math whizzes, what's the opposite, the inverse function of natural log? How do I get rid of this? The inverse of natural log. Thanks, Amina. And who is that? Anthony. And Louisa. Oh, lots of you. Ellie. Good. Oh, so it's E. So I'm going to take E to this thing. And what that gets me is just 0.16 molar over my variable, CT. And on the other side, I got to go E to this whole sucker here. Whoop, whoop. And I need you to probably do that and see if you get the same thing I do. So what do you get? Could you punch this out? E to the, what would that be? 4 times 3.35 is what? 1.4, something like that. So E to that, let me know what you get. What's E to this product up here? Mina may be getting the final answer. Are you doing the final answer, guys, or are you doing this? Because I got a different answer for that. All right. I got 4.06. And then I swap these two, so it's 0.16 molar divided by 4.06 equals, I'm doing it right, CT. Remember that switch, right? If I got equal fractions, I could just switch the top with one side with the bottom of the other. Good. So that's what I got as well. So I got altogether, I got divide that, and it should be like 0.0 something. 0.039 moles per liter, unless I put the numbers in wrong. Let's see if you guys get the same thing. Okay, and Sophie got that. If you got 4.05, it's okay. Just round it or whatever, and then put it back in. See what you get for your final answer. I'm hoping it's that. Okay. Check your decimal point, Oscar. I think there's another zero there. I hope so. I think it's 0.039 because it's 0.16 at the top divided by 4. Yeah? Okay, good. All right, good. Penelope got the same thing. Good. Thanks, everybody, for doing it. Let's do another part of it. So that's part A. I'm going to leave the stuff at the top and do part B. Okay. I hate this. There it is. Okay, here we go. Okay, so. Okay, part B, and you can just continue wherever you're at, is find the time for N2O5 to drop from 0.16 to 0.1. God, I kind of hate this little thing. 0.100 molar. Okay, here we go. Same bad channel, same bad place. Never mind, you're too young for that. So here's the relationship again. Natural log of CO over CT equals K times T. Plug them in. Let's check it out. Okay, so it's showtime. So natural log of, divide those. Your original's 0.160 divided by 0.100. Divide them, get the natural log, equal to the K we still got, 0.35 per minute, times T. So now it's really easy. We just divide this thing by the natural log of, what would that be, 1.6 divided by 0.35. And let me know what you get for T. Whoops, there's a big conversation and I totally missed it. Let's see. CT means in the time, the amount of stuff left at time T, or the concentration at time T. So T is the amount of time that goes by. So after 5 minutes or 10 minutes or whatever. In that other problem, you had to apply it because you can't leave it as natural log. You got to get rid of the natural log. And here we don't have to do that E of anything because here we can just do the natural log. We don't have to use E for this. So I don't need to use E on both sides. In fact, I don't want to because I wanted T alone, right? So T equals the natural log of this divided by 0.35. So let me know what you get. How much time is it, folks? $1.34 something. How about a label, Chelsea? All good, but no labels. 1.34 pumpkins, 1.34 Eiffel Towers, 1.34 minutes. Ah, good. Okay. Just keeping you honest, right? That's my job. Yeah. So that's the scoop. And again, and Sophie, I don't have to take the natural log here because, or the E here, because I can just take the natural log and get this to be a number. On the other side, it was my variable that I wanted was stuck in the middle here, and I had to undo the natural log by taking E to undo it. But I erased that already. And this one, I don't have to do that. Okay, now, part C. I'm going to leave my equation here, but erase my question, unless we got another question from you. Yes, Amina. Why are we using 0.1 as CT when we solve for CT to be point? Because it's a different question. For A, it was after 4 minutes, and for B, it's finding the time. So they're just A and B are different questions. So you're generally not going to use your answer from one into the other unless, okay? All right. Okay, so here we go. Find the something else. Oh man, look at that. I erased part of it. Didn't mean to do that. C, find the half-life. Now, what is a half-life? I think you had this in 9th grade, but let's remember. Okay, a half-life, it's the time for what? What is a half-life? It's the time for what? Somebody type something in. For decay, yes, Antonine, but what about decay? It doesn't have to be decay, by the way, Antonine. Now we're going to use the idea for any reaction. So what could half-life be? The time for what? Anybody. You didn't have to have it in 9th grade. Time for half of a little bit more, Bella. Half of the concentration to be half. Yeah, now we're closer, Amina. So the time for a reactant's concentration or amount to be half of whatever it was. Okay, now, Cheryl Smith gives you fancy equations for this. Don't memorize them. Use my way. I seldom say that, but I do now because my way is easier. Okay, half-life, right? Pick something. I don't care what, and take half of it. I'm going to pick two numbers. How about 150? How about 10 and 20 and 10? Or what I like to pick is 2 and 1. How easy is that? So my original could be 2 My time t could be half of that, 1. Duh. So don't use her fancy equations. Just put in these numbers and it works, because her fancy equations are worked out with 2 and 1, and they've got a new number you put in, and just don't. Just put them in. So I could just say natural log of 2 over 1 equals the k I know, it's still the same, 0.35 per minute, times the time, and that time will be my half-life. Isn't that beautiful? Go ahead and punch that out, folks. Let me know what you get. Type me some answers. How about with a label this time? And let's see what you get. Exactly, half of the sample to be K. That's right. Chelsea's already on the button. And let's see if some others will get there. Probably 2 sig figs, because you look at the K value, I gave you 2 sig figs, and that 0.35 has 2. So round it to 2 and see what you get. You're all giving me 3 sig figs, which is really sweet, but how about round it to 2, just for good measure, because that's what you'd want to do on the AP. Ah, thank you, Mina. So 2.0 minutes. I could write 1.98, but if they're really picky, which they were last year, you'd lose a point. They count significant figures. Now they're counted exactly, but only one time during the whole test. Pretty crappy, huh? So if you lose it one time and don't bother, that could be the time that they're grading for it. And they won't tell you ahead of time which problem they're grading for significant figures. So let's try and do it right every time. 2. Questions so far about using this equation? Nah, Aiden, be careful. It would, except for look at what they are. The original is on top. The amount for later is on the bottom. So it's not 1 over 2. The original is the bigger amount, 2, and then later on it goes down to 1. So even though it's a half-life, in this version of the equation I use, Cheryl uses a different version, but in this one, it's 2 over 1. Okay, good. Any other questions from you before we go on? I have another problem, but I don't think I want to do it because it's repetitive, and you probably don't need it. It's the half-life of plutonium, and if it's the half-life of plutonium, undergoing radioactive decay. It's what order? So if it's the half-life of plutonium decaying radioactively, what order is that from yesterday? What reaction order? You're listening closely? I told you. Radioactive decay of plutonium. What order is that type of reaction? Could be uranium, doesn't really matter. Yeah, it's first order. All radioactive decays are first order. Okay? So if you didn't memorize that, memorize it now. All radioactive decays are first order. Okay. All right, I'm not going to do that. Why? Because our time is limited. All right. Are we really that far? Let me make sure I didn't skip anything. We are that far, but we still got a lot more to go. How are we doing time-wise? Oh, man, time flies when you're having fun, huh? Okay, well, we can start this. We got 5 minutes, so here we go. Let's get rid of all this math stuff, and we're going to, breathe a little bit, okay? And we're going to do some with a little more theory and ideas, okay? All right, so everybody take a deep breath. I know it was fairly math intensive, but you guys were up for it. Everybody's wide awake. I like it. Good participation today. Yippee skippy, as my sister used to say. Okay, so we're going to talk about potential energy diagrams. PE diagrams. And it kind of goes like this. Let's take an example. Let's take CO plus NO2 forms CO2 plus NO. They're all gases. And now let's do the diagram. Okay, the diagram's going to look like this. On this side, we're going to have the potential energy. Now, I know a lot of you had that in physics. We're going to kind of review as we go along what it means in chemistry. Okay? For physics, it's like this, right? That's got PE because I'm holding it up, right? Okay. This is sort of like stages of the reaction. It's a little like time. Stages of the reaction. Okay, here we go. So I'm going to draw a line representing a PE diagram for this. You'd have to be given this. And I'll extend my X a little more. Okay. All right, for these sorts of diagrams, and you might have had these with Miss Galway if you had her or some other teacher, perhaps. Your reactants, the stuff you start with, starts here on this side. So on this side, I got CO and NO2. Your products are on the other side of this hill. So I got here CO2 and NO. What's in between is what you got to get over. Okay, so from here to here, from here to here, is energy. And that energy is going to be doing what? What do you got to do with these molecules? What did we learn in chemistry? Before I can make new stuff, what do I got to do with these molecules right here, the NO2 and the CO? Before I can make these, what do I got to do with these guys? Good. Several of you got them. You got to break the bonds up. Ellie and Chelsea. Right. I think I gave you this already last week. What's the name of the energy to help us do that? It's in green here. That's the amount of energy. So it's called the energy. Needed to break up, and I mean collide, bam, and break up. Okay, see, I did. So energy needed to break up reactants what's it called? The energy. Penelope has it. Thank you. It's the activation energy. And the abbreviation for that is E sub A. So I'm going to just call that right here. This is E sub A for this diagram. For the reaction going from the left side to the right side. Good. What do you think? Is this exothermic or endothermic, this reaction? What do you think? Just take a guess based on the shape of the diagram? Is it endo or exothermic? And while you're thinking about that, okay, Antonin has an answer. Products have lower PE, right? So it's a thermic reaction. Let's see what others say. Exo. Well, I guess the answer is exo. Everybody's right. Good. So think of like making something really stable. So because it's so stable, the extra energy is given off as heat. I don't have a spot for it on this diagram, or do I? Watch this. The difference between here and here and here it's something we had in our thermodynamics chapter. That's the change in what? It's the change in what for the reaction? Yes, Amina, that's the right answer. We'll come back to that. Hey, Penelope and Amina got it again. Good. So it's the change in heat. In parentheses, we called it, in long words, the heat of reaction. Okay, but Amina's right too. She said, you know what? It's kind of exo, then endo, then exo. So you got to put in energy and break up all these suckers until here they're totally broken up. Boop, 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 boop. Then the rest of it is giving off energy as new bonds form, right? And finally we're down here. But when I ask exo or endo, usually what I want is what's the overall idea? Well, if the overall is below where I started, then the delta H is negative, which you may remember, and it is indeed exothermic. Okay, I'm going to put a little star here as I run out of room to write. Right at the top, this is called the activated complex. Holy smokes, and I've kept you way longer than I wanted to. So let's do activated complex next time, but there it is. And I'll make sure Cheryl calls it the same thing. My apologies, I didn't mean to run quite that late. Okay, we'll see you on Monday. And next week, just to warn you, I'm probably going to make up a quiz in AP Classroom, and that'll be on gases. So from the end of book 1, chapter 8, I think it was, 7 or 8, on gases. So I'll probably have that and give you a reasonable amount of time to do it in Google Classroom. See you Monday. Thanks, everybody, for participating so well.